Welcome to The Explainer. Today, we're taking a deep dive into Chapter 14 of AI-powered search, and we're literally building a blueprint for a system that doesn't just find documents, it actually reads them and answers your questions. If you've ever looked at a modern search engine and wondered, how on earth did it pull that exact answer out of a massive wall of text? Well, you're absolutely in the right place. We're going to break down the whole architecture, from gathering data right down to fine-tuning a large language model.
Okay, let's just quickly map out our project blueprint for today. We're going to hit 5 key areas: the quest for answers, laying out the architecture blueprint, gathering materials, machining the parts, and finally, the final assembly. Let's get right into it.
Starting off with Section 1, the quest for answers, moving beyond 10 blue links.
For decades, right, traditional search engines really just gave us one thing, a list of 10 blue links. But to provide direct answers, we need to understand the difference between two types of question answering. Think about abstractive QA like a human writer. It synthesizes different sources and generates brand new text from scratch. But today, we are focusing entirely on building an extractive QA system. It's like a really smart automatic highlighter. It's not writing new sentences. Instead, it scans a document and highlights the exact snippet of text that perfectly answers your question.
Section 2, Architecture Blueprint, the Retriever-Reader Pattern.
So, to make extractive QA actually work without taking forever, we don't scan the entire internet or even our whole database all at once for every single question. That would just be incredibly slow. Instead, we use this genius 3-step pattern. First up, the retriever. Think of this as your reference librarian fetching the top documents that might have the answer. Step 2 is the reader. This is our AI acting as that highlighter, scanning those specific documents to locate the exact answer span. And finally, Step 3 is the re-ranker. It acts like a judge, sorting the best extracted answers so that we hand the absolute highest quality response right to the user.
Moving on to Section 3, Gathering Materials, Crafting the Golden Dataset.
Now, it goes without saying, you literally cannot train an AI without high-quality data. Before our reader model can highlight anything, we have to teach it what a correct answer actually looks like for our specific data. We kick things off with raw data, just real questions and accepted answers from a community forum. But manually highlighting the exact answer span across thousands of documents, that's incredibly tedious. So we bring in an existing pre-trained model to basically guess the answers, creating this semi-refined silver set. Then, to make it absolutely perfect, we move to Step 3 and create our golden set through human validation.
And honestly, this is where you see that behind the magic of AI is just the elbow grease of the human in the loop. The data flows from that pre-trained model into the silver set, and then a real person steps in to manually audit and correct those machine guesses. Only by meticulously verifying this data do we get our highly accurate golden set data frame. This step is absolutely crucial because it guarantees our model learns from completely trustworthy examples. Once we've got this golden data, we slice it up into batches, one for training the model, one for testing its accuracy, and a final holdout batch to make sure it actually works on completely unseen questions.
Section 4, Machining the Parts, Fine-Tuning the Language Model.
Okay, now we are reaching the most technical and frankly the coolest phase. Taking a generic, pre-trained large language model and fine-tuning it on our golden dataset so it becomes an absolute expert at extractive question answering. But before we start messing with the machine's dials, we have to ask a pretty fundamental question. How does the AI actually calculate where an answer begins and ends? Because, it doesn't read like you or I do. It relies entirely on heavy-duty math to spot an answer hidden inside a giant block of text.
Here's how it works. When we feed a paragraph into the model, it chops the text down into tiny individual pieces called tokens. Since these tokens are discrete values, the model calculates something called a probability mass function. Basically, it looks at every single token in the text and assigns it a probability score. You can see those tiny decimals, predicting how likely that specific word is to be the very first word of our answer. Notice the dark blue highlight over the word shoes? That means the model is highly confident that shoes is our start token.
Then, it does the exact same mathematical operation across the entire text all over again, but this time, it calculates a completely separate probability mass function. Now, it's hunting for the end of the answer. In this visual, you can see the highest probability, marked in green, lands squarely on the word conditions.
So, by mathematically combining those start probabilities from the first pass and the end probabilities from the second pass, the AI effectively highlights the exact span of text.
From the start token shoes to the end token conditions, the model successfully extracts the phrase shoes intended to closely approximate barefoot running conditions. And honestly, that is exactly how an AI reads a paragraph and finds your answer. Pretty amazing, right?
But there's a catch. We run into a physical limitation. Large language models have a strict maximum limit on token processing, often somewhere around 384 tokens. If a document is longer than that, we can't just carelessly chop it in half. What if the actual answer gets sliced right down the middle? To solve this, we use a technique called window sliding. We basically split the long text into overlapping sublists. This guarantees that the correct answer span will appear fully intact in at least one of those chunks.
Now, the model requires all of these overlapping chunks, or tensors, to be the exact same size when they're fed into the system. But obviously, the very last chunk of a document might naturally be shorter than our 384 token limit. To fix that, we add empty marker tokens. This process is called padding, and it just makes sure every single input fits perfectly into the model's architecture.
All right, with our data properly formatted, it's time to actually run the training. And to do this, we have to adjust the machine's tuning dials, what we call hyperparameters. We carefully set the epochs, which is just the number of times the model reviews the entire dataset. We set the batch size, which determines how many examples it processes before it updates its internal math, and we apply weight decay. This is a regularization technique to prevent the model from just blindly memorizing the training data, a trap known as overfitting. By dialing all these in perfectly, we teach the model to generalize, meaning it can accurately answer brand new questions it has literally never seen before.
Almost there. Section 5. Final assembly. Integrating the pipeline.
So, our language model is fully fine-tuned and validated. It knows exactly how to read. Now it's time for the final assembly, putting the pieces together into a fully working end-to-end search engine pipeline. When a user hits search, the system triggers 3 steps in a fraction of a second. First, we retrieve the documents, then we infer the exact answers, and finally, we re-rank those answers for the user.
Let's look closely at step 1, retrieval. The user types a question, and our traditional search engine springs into action. We tune this step for high recall, meaning we intentionally cast a wide net. We want to fetch the top 5 or maybe 10 candidate documents most likely to contain the topic the user is asking about. This instantly filters out millions of completely irrelevant documents.
Then, in step 2, inference, we take those top candidate documents and pass them directly into our shiny new fine-tuned reader model. The model scans the text, applies that window sliding technique if the documents are long, and uses that probability mass function math we looked at earlier. It infers the best candidate answers from each document and assigns a strict mathematical confidence score to every single extracted span.
Finally, in step 3, re-ranking. The system takes all of those candidate answers from the various documents and sorts them purely by their confidence score, in descending order. By doing this, we guarantee that the absolute most probable, highly confident answer is displayed boldly at the very top of the screen for the user.
By bridging this gap between traditional keyword retrieval and modern language models, you've completely transformed the user experience. You aren't just giving people a stack of documents to read anymore, you're giving them the exact knowledge they asked for. And understanding this entire blueprint leaves us with one final, pretty provocative question to ponder. What previously impossible problems will you solve now that your search engine can actually read and answer? Think about the possibilities for your own data. Thanks for joining me on this explainer, and I'll catch you next time.